Alright, so let me give you some overview of Fourier series. We start with the graphs of sine and cosine. These are the graph. This is the graph of sine x. And what happens if you put a 2 inside sine? It makes it contracted, right? It makes so the frequency goes up. By the way, we were calling this 2 as the angular frequency, right? So it oscillates more from negative pi to pi. And same thing for the cosine. This is the graph of cosine from negative pi to pi, and it oscillates more if you increase the angular frequency. Now, if you draw the graphs of sine and cosines for any angular frequency, here's an example given by 5, you can see that it has same amount of ups and downs. So here's something that's negative, that's positive, and we know that the integral has the meaning of net area, where you consider the negative ones as negative area, these as positive area. So if you integrate from negative pi to pi, all these cancel each other, and what's your integral? You'll get 0. Okay, so that's something that you should know, that sine nx and cosine nx, if you integrate over negative pi to pi, then you're going to get 0. Now, what if you multiply the sine and cosines? So if you multiply sine x and cosine, this is the graph that you get. Now, this looks suspiciously like another graph, and in fact, that's true. This is a graph of 1/2 sine 2x. That comes from the double angle formula of the sine. But you don't need to know that. Here's another one. Sine 2x times cosine 7x. That's more complicated. However, these are odd functions because sine is an odd function and cosine is an even function. So if you multiply an odd function by an even function, you're going to get an odd function. And that helps us in figuring out what the integral is from negative pi to pi. All right, so what is an odd function and an even function? First, even functions are functions such that are symmetric over the y-axis. So if you fold it, it folds evenly. So left and right, right and the left side fold evenly if you fold it. And such is true for cosine x, any polynomial with even power. And if you have polynomials with multiple terms, if they're all even powered, then their graph will still be an even function. Okay? So the left and right will match perfectly. In such a case, when you integrate from negative pi to pi, or from any even domain, from negative a number to the positive number, integrating just one side will be same as integrating from negative pi to pi will be same as integrating only one side and doubling it because of the symmetry. Okay? So you have this important formula where integral from negative pi to pi is same as integral from 0 to pi and doubling the result. Whereas odd functions have the property that it's symmetric over the origin, which means if one side goes up, the other side will go down exactly in the same way. So here's an odd function where if this side goes up, this other side goes down. Here, it's an odd function because when this side goes down, the left side goes up in this exactly same way that it goes down. Okay? It has the property that if you integrate over the symmetric domain, you're going to get 0 because when one side goes up, the other side goes down, so the areas cancel each other. Okay? And the odd functions and even functions have these properties. So if you add two odd functions, you get an odd function. Adding two even functions, you get an even function. If you have an even function and an odd function, adding them together will result in a function which is neither odd or even. In fact, most functions don't have any symmetry at all, so it won't be any of these. But if you know that certain functions have certain symmetries, it helps you greatly in calculating them. Okay? So you have all these rules, but rather than memorizing all these, it's better to think of examples. So if you forgot, what do I get if I multiply an even function by an odd function? you wouldn't know, but just think of an example of an even function, x squared. If you have x to the even power, you get an even function. If you get take x to the odd power, you get another example of an odd function. And so if you want to know what happens if you multiply even with an odd function, just think of an example. So here's an example of an even function, example of an odd function. Multiplying them, what did you get? You get x to the 5th power. What's that? An odd power. So it's an odd function. So that's what you know. You see, if you take the Taylor series of cosine, it's 1 minus 1/2 x squared plus something 1 x to the 4th. You'll see that it only has even powered ones. That's because cosine is an even function. Of course, the polynomial should only contain even powers. And Taylor series of sine has only the odd terms because it's an odd function. So sine x is x minus 1 over 3 factorial x cubed, and so on and so on. You will only get odd powers. Okay then, going back to this product of sine and cosine, because it's an odd function, the result of even times odd or odd times even is an odd function. What do we know of their integral? Is 0. Okay. So sine times cosine will always be 0, regardless of what these m and n are. Okay, next. What about sine times sine or cosine times cosine? Well, this one requires much more involved calculation. And you will see that when m and n are different, then this oscillating thing will actually add up to 0. So the integral will be 0. And the calculation is using this product to sum formula. You make this into the sum, and then if you calculate, it's going to be 0. But if they are equal, then you're going to get a value of 1. Okay, so a value of pi. So all these complicated calculations will lead you to the fact that if you multiply cosine times cosine, it usually gives you 0 as long as m and n are different. If they are equal, then you get pi's. Okay? These calculation results are called orthogonality relations. Okay? And we will use them later. But as of now, these don't look like anything useful. These are good for something called Fourier series. Okay? So we'll come back to the orthogonal relations later, but I'll first talk about Fourier series. Okay, so what is the Fourier series? Fourier series is the following. Here I have y equal to x squared, the regular parabola. Everyone knows the graph of y equals to x squared, right? And here I have the graph of pi squared over 3 minus 4 times cosine x. And that's the one in purple. So the blue one and the purple one are graphed together. They look kind of similar, right? Not very much? Kind of. Okay, so you're probably not very impressed at these two being similar, but in the next slide, I have the same thing, pi squared over 3 minus 4 cosine x as before, but I'm adding 3 more cosine terms. Okay, so cosine 2x, cosine 3x with some coefficient, cosine 4x with another coefficient. And if I do that, now the two graphs look very similar, right? So if you looked at their differences, their maximum error happens somewhere here, but they don't seem to be that much, right? Over here, if you computed the those two functions, they will be pretty similar. Agreed? Right? They'll be pretty similar. Right? Okay. Here's another example. I have a function which jumps from -1 to 1. So it's 1 on the right side and -1 on the left side. It's a constant function, and then suddenly jumps. Okay? Now, if you have these sums of sine x's, sine x, sine 3x, sine 5x, sine 7x's with some strange coefficients, and if you add them together, then you're going to get this graph, which, I mean, you might say it's not impressive at all, but it really tries to mimic this graph over here and then jumps over here and tries to mimic the other graph, right? If you added about 50 terms, I think this is 50 terms, so if you added 50 sine terms, this is what you get. You get some graph that starts down here and tries to mimic this lower part, and then on the right side it tries to mimic this one. Okay, so what I'm trying to convince you is that if you have any function, it doesn't even have to be continuous. You can add these sines and cosines with some coefficients, and you can mimic this target function as sum of sines and cosines. Okay. Why do you want to do this? Well, there are a variety of reasons. For example, your MP3 players make use of these Fourier series because these sine and cosines, they represent different frequencies, and the MP3 players works by changing your wave data, your music data, into different frequencies, and then you get rid of the higher ones, and you only keep the lower ones, and you still hear them fine. Okay? And it actually preserves less data than the original, without hurting too much of the sound quality. So that's what MP3s do. Even your MP4 players or any videos, they always make use of this sine and cosine, the Fourier series. Okay, so it's a way to shrink the data into smaller bits. So this might seem counterintuitive, but you see, to the computer, this is more information than this one, because this is like, what, just 50 numbers. You just have to remember these numbers, 50 of them, as opposed to having the values from negative pi to pi with a lot of data points. So at negative pi, it's -1. At something like -3, it's -1. -2.9, it's -1. So you have many values, all stored separately. Okay, and so this could be like thousands of data, whereas this one will be only 50, and this is approximately that. In real life, it's actually not like that. It's more like you have this very strange waveform, because your music is probably something very complicated, right? And then you're trying to mimic that by using only, say, 50 sine curves. So that really works. Okay, so it really works. All right, so the question here is, how do we get those coefficients? And the answer is, you do it by first rewriting the function f of x in this formal sum. So here's what we want to do. I want to represent the function as sum of cosines and sines. And to get the value of a0, here's what I do. I multiply cosine both sides, and then you integrate both sides. Now, if you integrate everything, you'll see that this is 0 because it's a multiple cosine function. How about this one? Cosine times cosine integrates 2. That's the case when m is 1 and n is 1, right? So what's the integral? You forgot? It was pi. Okay, so it will be pi times a1. The sine times cosine is always 0. Cosine 2x cosine x, if this is m is 2 and n is 1, what's the integral? 0. This will be 0. And you'll see that everything is 0 except just a1. So it will give you a1 pi by using these orthogonal relatives. So you can see it's pi here, right? So after everything is canceled out, you get pi times a1 equal to this. And therefore, you get a1, by dividing out pi, you get a1 as this. Now, if you multiply cosine 2x instead, and multiply and integrate it, then you'll find that a2 is 1 over pi times that. And repeating this for all of them, you're going to get the values of an and bn. So coefficients are found using the following formula. You multiply, if you want an, because an is in front of cosine nx, right? A2 cosine 2. You multiply cosine nx and you integrate, which results in pi, so you divide by pi. Same thing. bn, you integrate by multiplying by sine nx and divide by pi. So you can get everything. Here's an example, which we calculate for y equal to x squared. And this is how I got all those formulas. How much time do we have?
5 minutes.
5 minutes? Okay, good. All right, so here's an example that I want to show you. You can do this integral by parts twice, right? Or you can use tabular integration. And if you do it, that's the answer you get. However, this calculation does have a problem when n is equal to 0. When n is equal to 0, what is cosine 0x? It's just 1, right? So does that turn into sine or cosine when you integrate? No, that calculation has to be done separately. So even if we wrote down the formulas for an and bn like this. For an, a0, you have to calculate this separately. Okay, so that's what we have to do. And I'll just skip this calculation details because it's kind of straightforward. Everyone knows how to integrate x squared from negative pi to pi, right? So if you calculate, this is what you get. And then after plugging in everything, for the sines, you wouldn't get anything because x squared is an even function, right? So if you integrate against the sine, you're going to get zeros all the time. So you're only going to see the even powered ones. And if you added this, and if you drew more and more, you're going to get something very close to each other. Okay? Now, you might remember some resemblance with the Taylor series. Taylor series uses what to approximate? Polynomials to approximate, right? And Fourier series uses sines and cosines. Taylor series uses differentiation and plugging in 0 both sides to get the coefficient, right? Here you use integration against sine and cosine. Right? Taylor series requires the function to be differentiable, but Fourier series can even work when the function is not even continuous, because we don't differentiate, we integrate. That's the reason. Okay? And this is something that I don't really know. All right, and there's something called Gibbs phenomena. And see, sines and cosines are continuous, and you're trying to use continuous functions to approximate these non-continuous functions. And because of that, at points where it's not differentiable, or if it's not continuous, it has a big error. That's called Gibbs phenomena. And that's the cause of problems with MP3 players. See, if you change the music into MP3, the music that has lots of percussion, which kind of has these abrupt changes in the waveform, will suffer because of the Gibbs phenomenon. So for classic music where everything is smooth, MP3 players, it's really hard to distinguish MP3 file with a WAV file. Even when you make experts listen to it, it'll be hard. But for dance music or any rock music, MP3 won't do a good job because of this Gibbs phenomenon. Here's an example of the function that we drew. Now, we only had the graph from negative pi to pi, right? But if you extended it, graphed it from negative 2 pi to 2 pi, you'll see that. And the result is that when you have a function from negative pi to pi and make the Fourier series of it, you're going to get a periodic version of that function. Here's another example. Since we don't have time, I'll just show you what happens if you... This is called sawtooth. Okay, and then there's some more things that we can do with from negative L to L, but let's just stop here.